Hi there, and welcome to Toys in Space. On the 12th of April 1985, the Space Shuttle Discovery was launched from the Kennedy Space Center. It was carrying 7 astronauts, 2 satellites, and an experiment called Toys in Space. Now, this video contains footage shot during that 7-day mission, demonstrating how all of these toys behave in a zero-gravity environment. The first toy they looked at was the paper aeroplane. And this was tested flying it both forwards and backwards at different speeds and in air currents. They also tried to make it turn by banking it and flew it into solid objects to see what would happen. Here's what they found. The plane will fly further and at slower speed than on Earth, as it's not pulled to the floor by gravity. But it will not fly backwards, as it is not aerodynamic in this direction, and air pressure and density are the same as on the ground. The plane is easily moved by air currents circulating within the cabin. The astronaut next tried to fly it into a wall. As you can see, it bounces straight back. The plane can be made to turn by banking, and the effect of air currents can be shown well by blowing on it. The next toy was the paddle ball, and this was tested by paddling it in all directions. Now, there are 2 forces acting on the ball on Earth, the force of gravity pulling it downwards, and the elastic force pulling it back up again. And the astronauts wanted to see whether the force of gravity was necessary to make the paddle ball work effectively in space. As you can see, it's possible to paddle equally well in all directions in space, as the paddle ball only relies on elastic force. It's also possible to paddle the ball slower, giving the astronaut more time to correct his aim. When the bat is released, it moves towards the ball just as the ball moves towards the bat, showing that they exert an equal and opposite force on each other. Magnetic marbles will still attract each other in space because their behaviour depends upon the magnetic force between them, not on gravity. However, the effects will be seen much more clearly because there is no friction between the marbles and a surface, only air resistance. There is no limit to the length of a chain of marbles in space, as there is no gravity to pull them apart. Swinging them, however, introduces centrifugal force. When this becomes large enough, it will cause the chain to break. The most stable configuration for the marbles is in a ring. If 2 small rings collide, they are likely to merge to form one large one. This will happen more easily than on Earth, since there is less friction. They will also rotate about their combined centre of mass. This rotation is also shown when a single marble is thrown at a group. Even if the marbles don't collide, the magnetic force will still cause them to change direction. Watch this marble as it floats past the bulkhead. Next up is the yo-yo. Now, it may seem at first as if the yo-yo depends upon gravity. However, it can be made to work in space by spinning it with a flick of the wrist to give it its angular momentum. As you can see, the yo-yo works as well in space as it does on Earth. It can be thrown with varying speeds and in any direction. Many tricks can be performed better than on Earth. However, the yo-yo cannot be made to sleep at the bottom of the string, since this depends on gravity. If the string is let go before the yo-yo is fully wound, it will continue to wind back up to the top, while moving in a constant direction at constant speed. Gyroscopes are very useful in space, since when they're spun up, they stay pointing in the same direction. Now, this is an effect that's seen on Earth as the gyroscope stays standing up. Friction will start to slow it quite quickly, and as it does so, the gyroscope will start to wobble or precess. Now this is an effect that is only seen on Earth, not in space, because it completely depends upon gravity. Here the astronaut is setting the gyroscope spinning. You can see that no matter which end he tries to move, it will always stay pointing in the same direction. This means that gyroscopes can be used as navigation aids for spacecraft. The craft can be moved in any direction while in space, and as long as it's lined up with the gyroscope again before re-entry, the astronauts know it's pointing the right way. The gyroscope will spin for longer, as there is no friction against the surface. Although it will stay in the same orientation, the astronaut must be careful not to use too much force, as the gyroscope can still shoot off across the cabin. You can see here that although the astronaut is changing direction, the gyroscope remains aligned. The same would happen if it was the spacecraft that was rotating, instead of the astronaut. Swinging the gyroscope further demonstrates this. When it's not spinning, it will line up with the string. When it is spun up, however, it will stay upright while it's swung. Playing with a ball and jacks in space is very similar to playing on Earth, except that it's done in mid-air. However, the ball must be bounced off a wall, floor or ceiling because there is no force of gravity to make it fall on its own. One of the problems with playing with a ball and jacks in space is keeping the jacks in one place. As you can see here, they will tend to drift apart when released. The astronaut must open her hands very slowly to avoid giving the jacks kinetic energy. It's then possible to play the game normally, bouncing the ball off any surface. The astronaut must be careful not to disturb the jacks, because without friction they will be scattered across the cabin by the slightest force. When spun, the jacks act like mini gyroscopes, always pointing in the same direction. Some tricks performed by the slinky depend entirely upon gravity, such as walking down the stairs. It's therefore impossible to make a slinky do this in space. However, it can be used to show wave patterns more effectively than on Earth, since this depends only on the spring force, and gravity does not cause the centre of the slinky to sag. The slinky can be made to perform a single step in space, since this depends on the spring force. However, it won't travel any further. If both ends are released, the slinky will spin about its centre of mass. Wave patterns can be shown easily, like this longitudinal wave the astronauts have set up. On Earth, it's possible to set up a vertical longitudinal wave by holding just the top end. In space, this can't be done, as there is no up or down. Both ends must be secured. Here you can see they've set up a transverse wave. They managed to set up several modes. As you will see, the lack of gravity can cause problems in space, especially when there are too many experiments happening at once. The spinning top is very like the gyroscope, except the method of starting it is different. It's spun up by lifting and pushing the plunger, instead of using a cord. Starting the top is a problem in space, as lifting the plunger just lifts the entire spinning top off the surface. Therefore it must be held down with one hand while starting it with the other. This means it can't be spun as quickly. Once started, the spinning top will stay pointing in the same direction, just like the gyroscope. Lastly, we have the wheelo. Now, the normal method of starting a Yoyo does depend upon gravity. However, it can be made to work using only centrifugal force, allowing it to be used aboard a spacecraft. Here we see the astronaut starting the Yoyo using centrifugal force. If force is no longer applied, the wheel will slow down and stop due to friction between the wheel and the track. Unlike on Earth, it may stop at any point along that track. If the Yoyo is released, the momentum of the wheel will cause the whole thing to spin and move across the cabin. Although this experiment is called Toys in Space, it does introduce some very important physical concepts. For example, the difference between gravity and other forces, such as air resistance. It's important to remember that although there is zero gravity on a spacecraft, these other forces still apply, and indeed their effects can be seen much more clearly than on Earth, as they are not overpowered by the force of gravity. Thanks for watching. Bye-bye.